homework. And it's also, yeah, the cost.
All right, I think we'll get started. How's everybody doing? Good? Glad to get the first homework done and out of the way? All right, good. That just means that there's another homework waiting for you. 4 weeks out. No rest for the weary. Yeah, most everybody got it in on time, so good job. That's awesome. For a class this size, I was impressed. So good job. If you haven't gotten it in yet, get it in this week. It's only a 20% penalty. It'll become a 50% penalty if it's turned in later than that. Okay. So the next 3 lectures are pretty fun. We're going to kind of go through convolutional neural network architectures using the Imagenet recognition challenge as a kind of like a template for that history. So basically, the models that were the winners of that competition really became the standard convolutional networks that people used and still use today. And you'll find in most all of the deep learning frameworks that are available. So in their model zoos, as they're called, you'll find various recipes for different kinds of neural networks, and for the convolutional networks, it's basically all the ones that were winners or are slight variations on the winners of this competition. So it's kind of fun. It's kind of fun to see how rapid the progress was in just a couple of years, just as measured by how well those models did on that task. So that's what we get to do. There's three lectures on this. As a heads up, I won't be here a week from Tuesday. One of our TAs, Imagenet, will be covering that day. So, all right. So we already saw this picture. This is probably like the first successful convolutional network that really did something that was kind of like surprising and useful. It could read these letters and numbers. The data set this is trained on still is in use today. It's called MNIST. It's this larger data set of letters and numbers, and it's basically like they're all handwritten. And if I understand it right, it's like the actual characters themselves are taken photographs of like, or from photographs of letters that people have written, and sent in the mail. People used to do that. It was pretty cool. You have to wait a couple days and get your response. There was like a stamp on it that was kind of cool, kind of like a collector's thing. But yeah, you guys wouldn't know that anything about that. It's all right. Anyways, so. And then, the obvious application being like you could sort mail if you could have this like very, very good recognition system that could recognize handwritten letters and digits, and then you could say, hey, like this is being sent to this zip code or this city within the zip code, and you could do all this automatic sorting. So it's kind of one of these economic tasks that kind of drives the application of this research. And after our lectures, you know a little bit more about what to expect in a convolutional network. You have layers of convolutions. You have some layers of like what we call pooling, that's written as subsampling in this image. Some fully connected layers afterwards, and some scores that go into a cross entropy loss, if you're doing classification. The particulars about this, the conv layers here were they all had 5x5 filters, stride 1. As you'll see, 5x5 is kind of a larger filter. You don't see those much anymore, but 5x5. There was a pooling layer with 2x2 pool, stride 2. So just stride 2 in a 2x2 pool means you had these mutually exclusive pools that covered the whole feature map. You can see how this looks. It's a convolution pooling, fully connected. And yeah, so it's kind of fallen out of favor to do much with MNIST anymore, this data set. But it really, a lot of the early papers well, like a lot of machine learning just papers generally, but especially in neural networks, this was like kind of a standard task, but it became way too easy. And of course, you'll have access to this in some of your homework as well, and you'll see how very easy it is to do well on this task with very simple neural networks. Okay, so by the way, that data set, the MNIST data set, has like 70,000 samples in it. It's like 10, it's literally like just for the numbers. There's 10 numbers, and you get 10,000 or 7,000 examples each. And it's like there's a kind of a standard separation into like 6,000 training samples per image, and 1,000 per digit, and 1,000 rows. I think I have that right. But anyways, why all of a sudden, starting in 2012, was there like this explosion in the development of deep learning, and it sort of taking over all the other machine learning methods, especially in computer vision? Well, it really had a lot to do with the creation of this data set called Imagenet. And there was a group at Stanford led by Fei-Fei Li that basically put this thing together. And back in those days, I can't remember I think the publication date on the papers for this data set is like 2009. There's certainly people who were concerned about privacy, but there's a lot, you could sort of scrape the web and not really feel too bad about it. These days I think you're supposed to feel bad about it, but you didn't have to feel too bad about it. Since then, there's been a lot of kind of controversy around the way this is collected, and like the biases in the images and things like that. But nevertheless, the internet and some of the more popular apps that were being used, and the introduction of social media, really there was a place now where you could go and you say like, wow, there's like millions of images here that we can like put together into a data set, and we can drive real progress on our machine learning methods. And so Imagenet was born. So like there's Imagenet, which is the sizes you're seeing here. So 14 million images. They're all labeled with the like the objects that are in them, and there's roughly 20,000 classes. By the way, how do you label 14 million images? How does that work?
You ask people to verify whether they're
Yeah, Yeah, so this is like one of the other like innovations is like you could build tools where people you could crowdsource expertise from all over the place and say, hey, you label these 1,000 images and you label these 1,000 images, and then people get different sets of these and they're overlapping, and then you make sure that there's agreement, and if there's enough agreement, then you say, yeah, that's the right class. There's still some controversy in like the actual labeling of these images, but not too much. But yeah, so there's even tools now, kind of under the broad label of Mechanical Turk, that allow this, and people use it all the time. But whether or not it's the best way, I don't know, but it's certainly a way of getting this done relatively inexpensively. And then using this data set, a competition was begun, the Imagenet Large Scale Visual Recognition Challenge, so ILSVRC. And they created basically a subset of the 14 million, taking about 1/10 of it, 1.2 million training images, and 1,000 classes. So only of the 20,000 that were available, they chose just 1,000 of those. Fairly balanced with respect to the number of training samples per class. And so this became a challenge. Basically, it was like, we will hold a competition every year, and everybody who's doing research in object recognition in images can submit their best attempts at this, their best models, and then whoever does best on this held out data set will be will be the winner, and that's how we'll kind of keep track of the progress in this area. This started before things like Kaggle were available, but of course very soon after that you had like the competition websites like Kaggle and others come up that are like the very same idea. But this was in association with a conference that would happen every year to sort of mark progress in computer vision. So really this data set is really in many ways responsible for the progress that's been made in just in computer vision with respect to machine learning, in particular deep learning. Okay, so competition. So the data set's put together in 2009. First competition is in 2010, and what you're seeing is like the standard metric for this competition. So it says top 5 error rate there on the left, and what that means is the way that they decided to do the measurement was that to measure how well the model was doing was that your model would make a prediction about which class was the image was of, meaning that like this particular object was in the image. And your model was allowed to make basically five attempts at this prediction. So if you think about how we do prediction with softmax, that's basically giving you a likelihood per class. And you can rank those, right? And so like we usually, the class that's given the highest likelihood, we call that the prediction. But you could also take that ranking and then take the top 5 that were the top 5 highest likelihoods, and you say like, we predict that the class is one of these 5, or you could have top K or whatever. So top 5 was chosen here, and so the metric goes, if the correct class is in the top 5, is in your 5 classes that you predicted, then you got that test sample right, you got that classification right, and if it wasn't, you didn't. So the error rate here is the rate at which the correct class didn't appear in your top 5 guesses. Okay, so that's how this was measured. And so starting in 2010, you had kind of like the state-of-the-art statistical computer vision approaches, and 28.2 was the best top 5 error rate in 2010. In 2011, again another not deep learning, another statistical approach to computer vision. Machine learning involved, but sort of, but not neural networks. The best, some progress was made, right? The best top 5 error rate at that point was 25.8%. And then, in 2012, the winner comes in and substantially lowers that error rate to go from 25.8 the previous year to 16.4. And it is a neural network, a deep neural network at all of 8 layers. It was notable that a neural network won, but in particular, the amount of improvement was remarkable, and really, it's hard to understate how important this was for the trajectory that deep learning is on today. Like, this was a massive win for neural networks in particular, and the area of deep learning, and people all of a sudden kind of set up and said like, oh my gosh, this is going to work, and a lot of things were done, for the architecture here and the way this was trained to make it so that you could get to here. I mean, tons of work went into it. Apparently, there's 3 authors on here, but Alex Krzyzewski was really the one who did all the grunt work and trained, just model after model. You can read about this in some newer books that are coming out about the history of how all this happened. But anyways, just very impressive, and all of a sudden people are starting to take notice. And then what happens is, in subsequent years, we start just smashing those records, right? So the next year, this is actually not much of a change on the architecture from here, and all of a sudden we're at 11.7% top 5 error rate. Then we get a big change in architecture, actually simplification, and we get down to 7.3. We get a really strange architecture here, and it's a bit lower. And then we get our first, our first very modern neural network. This is a residual network at 3.6. Then some small kind of improvements on these for the next 2 years, and then after that it was we're basically, this is no longer serving its purpose. We have made all the improvement we can possibly make. And what's interesting here is to compare this to the error rate that a human makes, or a group of humans, the average error rate that they make, which is at 5.1%. So at some point, some poor humans were asked to go through the test set of this, for the competition, and pick from the 1,000 classes for each of the images, and the top 5 guesses, and they 5% of the time the top 5 guesses are wrong. And you can see that by 2015, we're really doing much better than humans with neural networks. Also important to see here is there's really substantial changes in the networks in many ways, but importantly, the depth of these networks changes quite a bit. So you can see how we start with 8 layers, which was amazing. People just couldn't imagine you could actually train more than 3 layers. You have 8 layers, then you're getting into dozens of layers, right? 19 layers, 22 layers, and then you get to the ResNets, which will enable you to get to hundreds of layers, even thousands of layers. They're not those aren't part of the submissions for the competition, but they enable thousands of layers. So in a couple of years, substantial progress here. And then what's really interesting is, at this time, in this same year, it's not in the slides, but this is the year that the transformer comes out. And now all of a sudden, the area of natural language understanding, natural language processing, natural language modeling becomes the area to do your deep learning research in, because of the massive language data sets that exist again on the internet, and the ability to this idea of a transformer architecture that allows you to really scale it up to hundreds of billions of parameters, which you don't often see in convolutional networks. So from here to here, computer vision was the place to be in doing deep learning research, and then from here on, it sort of switched over to natural language. Whereas today, most of the very recognized work is going on in natural language understanding, processing, whatever. there are obviously other camps you can go. You can apply machine learning. Other areas you can apply machine learning to, but these tend to be the kind of the two big dividers in terms of like types of data. Anyways, so let's get into this. 2012, the neural network that is the winner that year becomes known as AlexNet. I already told you about the image somehow was improperly set in the journal and it's cut off from the top. But fortunately, there's kind of symmetry here, so you can understand what should be there. Let's look at this let's look through this and kind of understand what this architecture is like. So it looks in some respect it looks like LayNet, right? The kind of the first successful convolutional neural network from, was it 1998? It's got convolutional layers followed by pooling layers and some fully connected layers. It adds one more thing that didn't appear in those before, and it has these. You'll see this norm 1, norm 2. So these are normalization layers, and these were important for training this architecture. We use normalization layers all the time now in modern networks, kind of like basically at every layer. The fact that this didn't have normalization layers at every layer is interesting, because they're now everywhere. But anyways, you have normalization, which was important here. So let's oops.
Question about that?
Yeah.
I feel like with making these algorithms in general, were they just like randomly trying multiple combinations, like convolutional layer?
Yeah, I mean not randomly, but yeah, they were.
Let's see what happens if we put 3,
Yeah.
4, 5 next to each other.
Yeah, that was apparently what like Alex had to do. Like this, this first author had spent all his time doing this, and of course it's not like there were these nice frameworks to do this on. Like it was all coded in CUDA from what I understand, and I mean it was certainly difficult difficult programming and probably very difficult to debug and all that. But yeah, all of that. So the architecture itself is like a hyperparameter, like a huge set of hyperparameters, right? So yeah, so like how there's a kind of question in there, which is, well, how do you choose it to be like this? Well, there's no like guide to that. You'll see through these next lectures, you'll see how you go from like this kind of architecture to very much more like standard components to build up deep networks out of. So like it becomes a little more rational in the sense of like, here are some modules or blocks that we're going to build the whole thing out of. How we're going to connect them together. Like when we want to reduce the spatial extent of like a feature map, like how we're going to do that, and we kind of follow these principles that are believed to be best practices. But of course, it's mostly like for convenience or like an application maybe of Occam's razor, where it's like you're trying to make networks as deep as you can, because that's where like a lot of the power, like representation power of these networks come from. And how do you do that kind of in a rational, systematic way where you're not literally at every layer saying, well, should this be a pooling layer or a norm layer? It's more like repeated elements over and over and over again. Great question. Okay, so the input to this must have had to do with like the memory constraints of like the GPUs they were using, but they resized their images to 227 by 227 by 3. So like in Imagenet, these aren't all the standard size. Like they're all different sizes. So your network. There are ways to make your network kind of able to deal with non-uniform input sizes, but it's certainly a lot simpler if you just have a fixed input size. So you needed to kind of pick an input size, especially here early on, and so this was chosen. And it has something to do with with memory constraints, and also like the sizes of the filters that they chose, and like what that got you down to, like in terms of like the feature maps before you went to fully connected layers. But who knows exactly why the choices were made? But it's kind of a weird number, 227 by 227. But that's what it was. And this first layer it was a convolutional layer. It had 96 11 by 11 filters. So 11 by 11 is enormous. It's huge. This will be the only place you'll ever see an 11 by 11 convolutional filter ever again in your life, probably. To compensate for having such a huge filter, there was a stride 4 was applied. So you had this huge filter, but then you'd stride by 4 pixels before you place down the next filter. So you can imagine if you just had a stride 1, this actually it's definitely not fully connected, but it's the larger that filter becomes, the more it looks like a fully connected layer. So the question is, knowing this, so like knowing what the input size is, and knowing what the size of the filters were and how many there were, and also the stride, what is the output? What's the size of the feature map? What's the size of the output from this convolutional layer? And the hint is you have that map that we've kind of looked at before. Image length, filter. You subtract the filter length, divide by the stride, and add 1. So we get 55 there. So what's the output size? 55 by 55 by 96. Good. Good. How many parameters are in this layer? Okay. Good. Yeah, it's pretty close. You forgot about the depth there, but yeah, that's good. So you think about each of your filters. There's 96 of them, so you have to have multiplied by 96. Each filter is 11 by 11, and it's depth 3. So 11 times 11 times 3 times 96 gives you the number of parameters. You might have 96 more if you include a bias per filter as well. Okay, the next layer was a pooling layer. They used 3 by 3 pools, but stride 2. So there's actually some overlap in these pools, right? So like think about 3 by 3 and you stride 2. That means that like the right edge, like when sliding this around, like the right edge of where the previous filter, like the pixels at the right edge of where the previous filter were, are now at the left edge of where the filter is now, right? Or if you move down, the bottom edge and the top edge. So anyways, you had this max pooling, 3 by 3, stride 2. What's the output volume? What's the size of the feature maps after this? Again, like the numbers are there, right there for you, right? So the important part here to remember in a pooling is that we're just reducing the spatial extent. We're not changing the number of filters. So we go from 55 by 55 to 27 by 27, but we still have 96. We still have depth 96 because of the choice of the number of filters in the first convolutional layer. So really quickly, after 2 layers, remember our input started at 227 by 227, and now we're all of a sudden at 27 by 27, right? So basically 90% reduction in the side length, and square that even more. So huge reduction already just in the first couple of layers of the spatial extent. So rapid kind of compression of the information that's in that image. How many parameters are in this pooling layer? How many? Remember the parameters that they're the trainable ones. How many parameters are in there? Someone's trying to say it. None. It's pooling. There's nothing learnable there, right? It's actually one of the nice things about it is that you get the spatial reduction without there being anything more to learn. Okay, cool. Right, so massive compression of the image in a couple layers. You don't actually, like in modern networks now where there are a lot of layers, you don't compress this fast. The compression is quite small, or you don't reduce the size this fast. But anyways, they did it. They won by a lot, so they could do the low-hanging fruit is the phrase that comes to mind. Okay, so here's more of the details. So here's what all the layers look like. We're not going to talk much about these normalization layers. They use the kind of normalization that we don't. That's just not popular anymore. We don't use it. There's much better normalization layers. So we're not going to get into it here in thinking about this architecture. But you can see sort of just the convolutional architecture. So like the size of the filters and the number of them at each convolutional layer. Also the striding, the padding simply just matches the size of the filters, except for notice that there was a pad 0 on this first convolutional layer. So really, like they were trying to compress this image really quickly. So typically you'd want to have like padding of size. What would that be in this case? 6, or I guess 5, so that you could have an 11 by 11 filter with its center at the corners and fit within that image. But they were far more concerned about reducing all of that. Why do you suppose that was? Why did they want to reduce the size of this so quickly? Yeah, just computational constraints. I mean, this was 2012. There weren't just like all these amazing GPUs built specifically for doing like deep learning. So they had what they had. This was actually trained on 2 GPUs, which itself is an innovation. We'll talk about that in just a second. It's the reason why this whole thing is like split in 2. But anyways, it's trained on 2 GPUs, not a whole lot of memory. So by doing this, your feature maps, the spatial extent of them is really reduced, and that allows you to have more filters. So you're learning more features, so to speak. But you can see, like in a couple of layers, we really quickly get our go from 227 by 227 to 6 by 6 with a depth of 256, and then we just we take this this is a spatially extended feature map. We stretch it out, and we then that's how the input to a couple of different fully connected layers of sizes 4096. Again, like why choose that? It's not really clear. But then of course you do have to have your last layer producing the output size has to be the number of classes, right? So in Imagenet there's 1,000 for the competition subset. There's 1,000 classes, so we need to have 1,000 scores. So there, that you get some kind of sense of how that was built. Lots of innovations, like I mentioned. We're going to go through a couple of these. So we've already talked about ReLUs. This really was like the first kind of successful use of ReLU. Jeff Hinton, who's on this paper, said like it shouldn't work, but it does, and and that's why for like a lot of the reasons why we do the thing in deep learning is often because it works, and so it did work. There's your normalization layers. We're not going to talk about them. We will talk about normalization throughout these next couple of lectures, like the kinds of normalization we do now. But one thing I want to stop and focus on is the kinds of regularization that was done for this network. So one of them is this idea of data augmentation. This is really, really important and used ubiquitously in training neural networks, this idea of data augmentation. So remember, the idea of regularization was some preference we had for the weights. That's kind of how we introduced this idea, and we add a kind of penalty term to the loss that says, the lower this is, the more these weights look like what we want them to look like. And often these are penalties for the weights being too large in certain ways. And remember, like the thinking behind that is large weights really contribute, like typically translate into like very wiggly output, you know, like so the ability to say overfit to training data, you want to prevent that. You want to make it so that those weights don't have, you know, they're constrained to not wiggle as much, or the model can't wiggle as much, and so reducing the weights allow that, and that gives you this kind of smoother interpolation between training points and smoother extrapolation outside of the training points. But a totally different idea that nevertheless is a kind of regularization is this idea of data augmentation. And again, regularization, the effect of regularization should be to improve your network's ability to generalize to unseen data. So anything that kind of like, any procedure or method that allows that to happen is often called regularization. So what's data augmentation? So remember what we're doing. So we have a data set, and we're doing supervised learning right now. So you know, we have a data point, and we have the label associated with that data point that we're trying to learn. Like basically, you know, we're learning this function from the data point to that label, right? So we have a convolutional neural network. It produces some scores. We want the largest score to be given to the entry in our output that corresponds to the right label, in this case cat. Okay? The idea of data augmentation is I can do a lot of things to this image, and it's still a cat in that image, right? So I can transform this in all kinds of ways. I can do very simple things, right? Like just flip along, like, you know, like certain like vertical or horizontal axes. I can randomly crop these things. I can stretch them. I can do all kinds of things. Now, let's see. For the for Imagenet, what they did was to crop and scale these images. So what they did was they took their image, they resized it so that whatever was the shortest side of the image, you know, like say if it's like, you know, the width is shorter than the height, whatever that width now was resized to 256, and then they randomly sampled patches of size 224 out of here, and that became the input to the networks. And you just do that over and over again. Remember, like what you're doing is you're going through training, and you're going through your data set. Like you're trying to, mini batch training really wants, you know, like the theory is that you're just like, you know, randomly sampling with replacement from your training data mini batches, and you're estimating your gradients from that. Here we're not doing that. Here we are typically we're randomizing like the order of our data, and then we're kind of running through that randomized order in chunks of whatever the mini batch size is, so that you run through all your data and you start over and, you know, re-randomize and do it again, so you get different batches each time. So every time you get to this image, you're going to do this kind of resizing, but then you're going to get a different sized crop. And this, so, you know, like, so sometimes what that means is you could get, like, for this particular image, you could get like the face of the cat. Sometimes you could get the body of the cat down below, just like the legs or the, you know, tail or whatever. You could just get the middle of it. You could, depending on how you do some of the resizing, you could just get the size. Like if, you know, there's lots of ways in which this is done. You can maybe just get like the ears or whatever. But, you know, in each case, you're saying, here is a cat. You know, learn to classify it appropriately. So you're really, in some sense, like, you know, really increasing the data set size by a lot, by multiple factors, and you're making the task a bit more challenging, because, you know, instead of like being able to see, say, the whole object, you're making it focus on, like, you know, certain subsets of that image, which maybe only contain certain portions of the object. So the models become much, much better in this case. Now, what do you do at test time? If you're training like this, what do you do at test time? At test time, you do something very similar, but you just you have a very specific way of creating those crops. So the way that this was done was to create the patches where we take like the patch of that size in the upper left-hand corner, the upper right-hand corner, the bottom right-hand corner, the bottom left-hand corner, and then directly in the center. And then we also do reflections of those. So we get 10 kind of crops of this image total, 5 plus the reflections of each. And then we can put those into our network, and we can forward those through, and we can get our softmax output. So this is giving us the likelihood that the image contains these objects from the 1,000 classes. And then what you do is you kind of ensemble these together. You average all those softmax outputs together from those 10 different crops, those 10 different patches, and then you predict using that averaged softmax. And this actually really works well, and it's used all the time still for tasks like this, and is modified for other kinds of tasks. There's lots of things that you could do. So like that's like the basic technique for how they trained AlexNet. What are other things you could do? Well, if you slightly change the colors, the contrast or the brightness, there's still a cat in that image, right? Like the image looks different, obviously to us, but there's still a cat there. So like the array, like the actual array of numbers that's being given to the network is different, but like the arrangement is such that there's still a cat there. You had a question?
Yeah. For the training and test sampling, so the important part there is that the test data is like engineered augmentations. Data like manually done augmentations as opposed to the training set where all the augmentations are random.
Yeah, I mean it's just that you want to the reason for random in the training is that it's just kind of like it's just a very simple way of augmenting, right? Like you want to just get you're going to see this image once during the epoch, and you just want to get like a random kind of augmentation of it, because you're going to see it if you train for 100 epochs, you're going to see it 100 different times, you're going to get 100 different. But like here, what you're trying to do is you're trying to say, okay, I want to build up like a body of evidence for what the class actually is. So, but I have to follow some of the parameters, like what's the actual like size that the models, the size of the image that the model's expecting, and things like that. So, since these were smaller than the actual size of the image, the idea was let's cover it, right? Let's get the corners, let's get the center, let's get some more, let's just do the horizontal flips, and of course it doesn't have to be that. You could have done it differently. You could have maybe done the vertical flips as well. I don't know, but those are all called test time augmentations, and it's just a way of kind of building up a bunch of evidence. Now you could trick yourself, right? Because in some sense these are really correlated. Like all this information is correlated, so it's not like you're getting these independent samples of like each of these is like adding. It's not like they're independent pieces of evidence, but it does help a lot in terms of improvement to generalize outside of the training data. So there's all kinds of things you can do. I don't know. It's not even worth really listing them anymore, because there's like amazing packages out there that just all kinds of augmentations you can do, ways of rotating and stretching and scaling and like all kinds of color and contrasts, like transformations, all kinds of like kind of crazy stuff. Smearing, like you could add Gaussian blur to kind of make the image less crisp, so it makes a little bit. You're making the task harder. You don't want to make it too blurry, so you can't tell at all what's going on. Ideas of like downsampling and things like that. There's all kinds of things that you can do. And the best thing to do these days is just like go to PyTorch has a library within it that's for all these augmentations. There's 4 PyTorch. There's a really well-known one called Augmentations that people use because it's pretty fast. Has a nice API. There's all kinds. It's just great to just go through those and just see like what are the augmentations that are provided in a framework, and you can just read through them and say, oh, that's cool. I would never thought of that. That's interesting. That really works. I don't know. And again, you know, like, what does it mean to work? Well, you try some things out. Whatever gives you better, you know, test metrics works. And if it doesn't, it doesn't work. So it's really empirical, which is problematic in a lot of ways, but it is the way that we make progress here. Okay. So that's one idea of data augmentation, and really, you know, now that you know about it, you should always expect to use data augmentation when training neural networks for whatever task you're doing. And you know, thinking up like for images, there's like a set of things that you can kind of think up to do, especially for natural scenes. But you know, different data types, whether they're, you know, images or language, or whatever, have different proper ways maybe of augmenting, and you know, there's kind of a whole art behind all of that to learn about, but you should always be thinking about augmenting. It always helps.
The 224 versus 227 kind of comes to me up.
Yeah.
Is that intentional? How do you go from 224 to 227?
Yeah, so the reason is that it did use 227, but everything after this decided to use 224. So, yeah, so like, it's again one of these kind of like accidents of history, so to speak. But like all like, if you go look at anything now that is done with Imagenet, you'll see rescaling to like the typical input size is 224. It doesn't have to be like, but if you go pick a model out of like the PyTorch model zoo that was trained on Imagenet, it'll expect images of size 224. It was basically said like 227 was a really goofy number. That's really
so
that's
the
really all it
idea
is.
with the cropping is just to crop it to your input size.
Yeah, the idea with cropping, rescaling, whatever, is that you have to match your input size, whatever you choose that to be. Now, like 224, there's nothing special about it. 227, it's just what was chosen. You might have, for a totally different application, might want to use much bigger input size or much smaller. These days, where we have GPUs with tons of memory, you can afford to have much larger input sizes. And if that helps, you should probably do that. So, okay, so that was one kind of regularization that now that you know about, you should be planning on using all the time. Another regularization used here was this idea of dropout. Now, dropout is super interesting. So the idea of dropout is that, so you have this neural network, and you know, at every layer it's got a number of neurons that are connected to the neurons from the previous layer, these units. Dropout says every time that we do an iteration, that we do this forward pass and then the backward pass to update the weights, we are going to drop out a certain percentage of those neurons. We're basically going to say they're not going to take place in the computation of the final score, say in the classification task. And we're going to randomly do that. We're going to randomly do that. So it's very typical to pick a percent of dropout. So this says 0.5 is common. Actually, it's more common these days to have it to be lower, but this is one of those hyperparameters. But and then at every layer you say I'm going to drop out that percent of the neurons. So if it's a half, you expect to see a half of the neurons randomly dropped out. The way you do this, right, is that you have a bunch of Boolean parameters, basically you're flipping coins with the right probability, the bias in the heads or whatever, and then if it comes up one way, it's included. If it comes up the other way, it's not. And so you just have the outcome of that is that you just have a subset of your full network that's contributing to the calculation of the scores that are then used to do the task.
And dropout, it's a layer hyperparameter, right?
Yeah, it's usually done at a layer level so that you because there's a problem. So typically these are always we don't have fully connected layers, but we typically have like parameters from the previous layer, or like output from the previous layers is fully connected to the output of the next layer through your parameter mask. So that's typically the case. And if you like you can't drop out a whole layer, for instance. That would be really problematic. You'd have, that wouldn't make any sense, right? So you do this usually at a layer level so that you don't have that happen. I mean, it's not like forced on you to do that, but that's like just typical. Yeah.
So what is a neuron? Is that like the numbers in the filter or the numbers in the
No. So the edges are the numbers in the filter, right? Because these are things that connect you from. So like think of like maybe this being the first layer. These are all your pixel values, right? And then this is your feature map, like after the the convolutional layer. I mean, it's not a convolutional layer, but that's the idea, right? So those are the neurons, and these weights between them is like the connectivity between those two neurons. So think of it as units or nodes or whatever, but it's input to output.
So the arrows represent
The weights.
images?
Yeah, exactly.
So if we're using a ReLU activation function, this would really only affect nodes that are giving signal, right? Because everything else would be 0.
Yeah, that's right.
So
Once we put in normalization too, you'll see that the way you have to change a little bit how you think about that, because that's gonna reestablish the idea of normalization is you're gonna force some statistics on the output or on your feature map, and so you can recenter that around your mean and things like that. But yeah, you're right. I mean, if this was the output if this was negative coming into this and then you had a ReLU, it wouldn't have mattered anyways. But
Sorry, I can ask questions.
no, that's great.
So when it says randomly set some neurons to 0, that's not actually setting them to 0, is it? Like when you're going through an epoch, you go from one end to the other, and back propagate
Well,
accordingly.
you do this at every single iteration, so every mini batch.
Okay.
Every mini batch. So you choose 32 images, that's your mini batch. You're gonna get some get some random dropout. And then the next 32 images you're gonna get a different random dropout. Because you're gonna keep sampling, you're gonna keep flipping coins basically.
But then ultimately from iteration to iteration, technically it doesn't set that W to 0
No.
specifically, it just ignores it for that iteration.
Just that iteration, yeah. Good question.
So are we dropping some batches from input data as
No, typically not.
So what happens?
Yeah. Don't worry about it. Input's down here somewhere. Where there's a connected inputs. Yeah, typically you don't do that. Good. That's good. Good catch. Other questions? Yeah.
When you were showing the diagram for Weight, you have a Gaussian connection at the end. Is that sort of like dropout?
No.
It's not fully connected.
No, it's not. Yeah, it's something that you don't see anymore. Think if it was a kind of activation. It's something you don't see anymore. But you could go find that paper and go check it out. Have a lot of fun. Okay, so this is it. So every single time, so think about what's happening here. Every single time, every single iteration, you're trying to produce, the correct scores, or relative to each other, that the correct class has the highest score. But every single time you're doing it with a different subset of your full network. And then when you do back propagation only occurs, along these weights that were included, right? So some of these weights in an iteration aren't being updated, right? So different ones at different times. So raise your hand if this feels chaotic and crazy. Yeah. Yeah, does it seem crazy that you'd even try to do this? Yeah, it is kind of crazy. And actually, if you had really small networks, I think this would be absolutely brutal. But we don't. We don't have really small networks. We have there's a lot of parameters, and the sizes of the inputs and the outputs are actually quite large at every layer. So this really helps a ton. So what's going on here? Oh yeah, this is something. This is the algorithm. How you might do this? Draw draw your random number, apply that to to create a mask, drop these things out. Anyways, there's a lot of ways to implement this. What was I going to say about this? I forgot. Oh yeah, like why this works. Was there a question over here? Okay, so why this works. Anyways, this is how you might think about implementing it. Why does this work? How can this even be a good idea? Well, the good news is that we're actually going to be training for a long time, right? Like we're going to be training for many epochs, like lots of iterations, right? Like hundreds of thousands of iterations usually. So what happens here? So what you're forcing to have happen in this case is that there's got to be like a redundant encoding of the information needed, from the image to get the correct class in your, like across lots of your weights. So what this does prevent happening is there being really like certain weights that just correspond to certain like concepts or subsets of concepts or something like that. Depending how you do the dropout, you can be really aggressive. Like this is really forcing the network to sort of, use its resources wherever it can find it within that subset. And therefore gives you this very distributed, as we think about it, like very dense representation of the information in an image, like in all the resulting features. Like if you think about like, in AlexNet where you have these fully connected layers at the end under size 4096. Like what information's in each of those numbers? Well, by doing dropout, you're really forcing like that information to be like densely distributed across like most or all of those numbers. Whereas you could have been the case that like, say one of those numbers corresponded to, like a certain feature. I don't know. Like it doesn't really turn out this way, but like, has a cat ear or has like, fur or something like that. But like that kind of interpretability maybe sounds kind of good. So like, why this redundancy? Why is this even a good idea? Or like, it does help. So why? Why did having these dense redundant features? Why does that help?
Because while having an ear, we can say that as a single feature. Like there are different types of ears, or there are different ways you can look at the ear and things like that. So if you have one ear that's pretty good at picking at this angle or this color scheme or whatever, and another one that's a different type but ultimately in the same position, I don't know. You ultimately cover your bases for the multiple ways that you're going to be presented.
Yeah, that's right. It's like it's becoming your network is becoming very robust to these concepts. Like it's forced to learn them, but it's forced to learn them like, think about it as like different parts of its brain, right? Like different parts of your brain. So it's not just that it's like this one neuron that has this and if that neuron disappears, you'll never know that concept again. It's like being distributed. That, like this robustness is actually really quite good. And another, let's see, I can't remember if I have, another interpretation of this that's really important is something like the following. Each of those subnetworks is like its own predictor, right? It's like its own network that's making a prediction. And every random dropout will gives you this different subset. So like, let's imagine that every subset now is itself a really good predictor. When you bring the whole network back together and you use the full network to make the predictions for your class, it's like you have this large ensemble of all these subnetworks working together to make your final prediction. And ensembling, as you may know from your own experience, or you may have picked up from like a couple of times that it's been said in this class, ensembling of multiple good predictors gives you an even better predictor usually. And so you're kind of getting that as part of using this technique, is that each subset, each subnetwork is actually a very good predictor for whatever it is that you're trying to do, whatever task. So so it's really good that way. So what do you get out of this? You get a very robust network with robust redundant features. This leads to better generalization. This leads to better ability to predict the class outside of your training data. And that then becomes a kind of regularization. So that's all good, you know, that's all good. What do you do with dropout at test time? So remember, at training time, this is always the interesting thing to think about. So there are fundamentally two different phases here with neural networks. When during training and when you're testing, and you know, certain kinds of procedures like this, you know, need to be dealt with appropriately. So when it was data augmentation, we wanted to take advantage of the fact that, like, the network's been trained on lots of different augmentations and recognizing those, and so we want to build up kind of like a body of evidence for the correct class. Here, what we have is we've got this kind of like, you know, we've got this kind of randomization where we're dropping out these units from the network. We're getting these subsets. So, like, what's going on here? Well, one way to think about this is that there's a kind of like there's a kind of parameter. So every time we train this here, there's a kind of parameter that tells us, like, which of the subsets that we're getting, right? And the idea is we want to ensemble all of these subsets together. So this kind of looks like an integral where we're trying to make a prediction for just the input. What we really have is like this whole ensemble of models. We want to, like, integrate those all together to give us, you know, the combined, you know, all the evidence from all of these different models to give us this combined output. You know, where, you know, this represents something like, with what, you know, given this configuration of the network, like, what weight that should contribute to the output. And, you know, in our case, this is going to be some constant. But, like, in general, this seems like this is kind of hard to do. So how do we deal with this? How do we approximate this integral at test time? So the answer is we have to scale things appropriately. So let's just think about how, like, the input of two inputs to an output, how they come together in, like, a very, you know, simple network to give you, you know, say, like, the expected output. So the way this works, quite simply, is, you know, we have these linear operations of our input times the weight plus the other input times its weight, you know, together gives us the output. But at training time, what were we doing? We had this probability of dropping these out, right? So at training time, there, you know, if we were using 1/2, like, if the probability was a half that we included a weight or we didn't, then there was a 1/4 chance that we had both the weights, a 1/4 chance that we had just the first weight, a 1/4 chance that we just had the other weight, and a 1/4 chance that we had neither weight. So if you do all the math here, what you see is that this 1/2 came out. You can factor this 1/2 out, and so you have what you would naively do at test time. You have 1/2 of that. So this is a problem. Like, this dropping out means that the expected output is scaled differently, and this actually can have really drastic effects. In fact, you're going to see this in your homework. It's going to have really drastic effects on what you end up predicting if you don't have this scaled right. So what do? So the right thing to have done is, instead of just naively doing this, we just need to multiply by whatever our dropout probability is, and we're rescaled back to the correct probabilities that we had at training. And this is done in a really simple case, so you can just kind of, like, get an intuitive understanding of how the math works. But you can also prove that, just in general, for the kinds of networks that we use, like these, in particular, applying the dropout to these convolutional layers, that this same scaling also should be applied. So if we think about what this looks like at test time, we just need to, if we're doing dropout at a rate of p, we just need to multiply all of our outputs by that p. And if we do that, that scaling actually gets us to the right kind of, like, units for the activations that were the same units used during training time, and now your data doesn't look like it's out of sample, it looks like it's in sample, and everything's going to work well. Does that make sense? what we just did here? There's a kind of scaling issue if you don't pay attention. You just kind of, if you naively just use the whole network unscaled to at test time.
You said it would make your data look out of sample?
Right. So it would make it look like out of distribution. So your training data is like in a certain kind of distribution, and by doing the dropout, it's sort of like all the activations were expected to be at a certain of a certain size, or like a distribution of sizes. But at test time, these were now like 1/p too big, and that puts it out of sample or out of distribution. And so the model, we hope that our model will generalize to all cases, but that it'll have a hard time doing that because it hasn't seen activations of those sizes. So you need to rescale these activations to put it back into distribution, to take into account the fact that you did this scaling. So it's a subtlety here that needs to be dealt with.
You do it every layer.
Where you did dropout.
Oh, okay.
Yep, exactly. And you use that dropout percentage. And oftentimes you just fix this to be the same, dropout rate for all the layers. But of course you could change that. So at every layer you have to use the appropriate dropout rate.
Shouldn't it be 1 minus the dropout rate? Because if it's not 0.5, right? Because if you want to scale it down to like that, something correct? Because if you have like a dropout of 0.25.
Yeah, so you're saying it right. So like we keep saying dropout rate. It really is 1 minus this. So like P is like the keep in rate. Yeah, good point. That's a great point. Okay, so this is now kind of like reworking of that code that we saw before. The right way, if you're dropping out with rate or you're keeping in with rate P, then you're going to need to scale at rate P. What's actually done in your code, like from PyTorch or TensorFlow, is to not do this at training time, at test time, but at training time to do the appropriate rescaling by dividing by that P. So because all these operations are linear, this will just kind of pass through, and and the rescaling will be such that we don't have to do any scaling here and be at the right size. So it's just like, by keeping things at a rate P, and then dividing by that again. That's sort of like we're losing that amount, and then we're kind of like blowing the size back up again because we divided by something less than 1, and so that puts it right back on the same scale that it should be at. And so at test time we don't have to do anything, and that's actually typically what's done.
Does that make it so at inference time you don't have to change your projection?
Yep, at inference time you just pretend like nothing ever happened. Yeah. So you could become like numb to all these things that are happening, which is fine. But at some point maybe something will go wrong, and you'll think, oh yeah, I remember that thing. Dropout. Just being aware of kind of how these things are implemented. Dropout is really popular. It's still used a ton as a regularization for training neural networks of all kinds. Yeah, and so just it was kind of maybe like a weird way to motivate it, but this is very common. So like the idea of regularization is to introduce a kind of randomness, data augmentation, dropping out of network, lots of other things that you could do. And then at test time, the idea is that you want to average out that randomness. So you can think of like the taking of 10 patches of an image, like what we did for data augmentation, and averaging all those outputs together as a way of like averaging over the randomness, of that happened during training, of like choosing random patches, right? So it's a way of kind of putting yourself back on those, like averaging over the kind of randomness that you introduced at training time. So it's a really common pattern that you'll see in different kinds of regularization. Okay. Questions on those two things? These are really common. You'll see them all the time. You'll end up using them in your own neural networks, in your own training. They really help in terms of improving your model's ability to generalize to out of distribution data.
I have a question.
Yeah.
You're scaling the information. Are you scaling per, I guess, I don't know if it matters if it's an operation. Are you scaling per layer or are you just scaling the output scores?
I mean, you're scaling the whole layer like it's output scores. Yeah. Okay, so we've gone through some of these different things. This used a batch size of 128. It used stochastic gradient descent with momentum, with a parameter of 0.9. Remember we talked about that last time? Here you go, one famous use of stochastic gradient descent with momentum. Let's see. Here was the learning rate. So it started off at 10 to the minus 2, and then reduced by a factor of 10 every time that the validation accuracy, so accuracy on your test or validation data, plateaued, right? So if it like wasn't learning anymore, then learning. So learning is typically means that your loss is dropping, right? You're getting better at your task. So if you stop getting better at your task, then you drop the learning rate, and then you tend to see that you learn some more, because you're taking kind of smaller steps wherever you are, and then you do that again a couple times, and then usually you're done. And then what's very, very standard of an L2 weight decay, right? So like that squared term that you did in your homework with a parameter of 5 times 10 to the minus 4.
That's regularization.
There's another regularization as well. Yeah, exactly. It's called. You'll see this all the time in like the frameworks that you'll use. It's called weight decay, because it's like making the weight smaller. The effect of the regularization is to make the weight smaller. So it's called weight decay, but it is that L2 regularization term that you got to do in your homework, and hopefully you back propagated through it properly. Some of you weren't, and you came and talked to me, and now you are, which is great.
Does that mean your regularization, you do more and more regularization as you go on, or less and less regularization? Like that?
It's just a regularization term, right? Like it's a penalty for having too big weights. So it's the same. You add that term with a weighting of 5 times 10 to the minus 4. No, you don't change. You could change it over time, but it's not typical to. It's just keep it fixed. Right, and this is like a kind of, it's a way of kind of balancing the effect of the weight decay with the actual loss term from the task, right? So like when the loss term, like if this is at like kind of standard units of like say 1, when the other loss term gets down to 5 times 10 to the minus 4, then like those two things are kind of balanced. But typically this is going to make this smaller than the loss, especially when you're starting to learn, than the loss from the task, like the classification loss. And so most of the weight updates at that point will be about reducing the classification loss, and it's only when that gets smaller when this starts to kind of take over, and have a greater effect. I mean, it's always there, but it's proportional. So like I guess if you start off and you did a random initialization where like your weights were huge, that initial term would be very large, and that would be the first thing to happen. Would be like, well, let's get those weights and make it small, and then we'll start learning. But whatever, it's just, remember, it's just that hyperparameter to decide how to combine these things. Okay, so what's this thing about this weird picture? Besides it being like cut off at the top, notice that like these filters are split in 2, right? We said this was a convolutional layer with 96 filters, but you can see there's 48 here and there's 48 here, and these were trained on good GPUs at the time. They only had 3 gigs of memory. A lot of memory was being used to store all of these parameters. You also needed to have like a decent batch size, which was 128 here. So there was an innovation here where they basically split these filters for different convolutional layers and put them on different GPUs, So like half the filters, their weights were on one GPU, half on the other. So it wasn't. It's not it's not exactly this network that was trained. It's actually, a slightly different version where some of you had kind of like two tracks being trained, and then every once in a while they were brought together. So let's see. I think I have my next one. Yeah. So conv layers 1 and 2 and 4 and 5. These were their feature maps were on the same GPU. Let's see. Wait, hold on. Doesn't seem to be the thing to say. Oh yeah. So sorry. So what we're saying here is that there were 48 of the 96. 48 of those were on one GPU, and they were connected to not 256 but 128 of the filters from the second layer. And then at the third layer, they were all brought together, and you actually had that kind of a sharing across all of them. But then they were split again. Again, this was just for like computational efficiency. You wouldn't do this anymore for this size of network because we have lots of memory on our cards. Like modern cards can have 80 gigs of on chip memory. So like lots and lots more than this. However, for huge networks, like these hundreds of billions of parameter networks, they are split up on different GPUs to be able to train them because they are too big, but they're split in different ways than this. But anyways, this is this allowed them to get a bigger network and allowed them to do better on the task. Yeah. So at this layer and then the fully connected layers, these were all on. These were all the parameters were shared across both of the cards. Okay, so like top 5 scores from before. Best score was 26.2. A single AlexNet had a top 1 error rate of 40.7. A top 5 error rate of 18.2. Remember, it was actually lower than that. And what did they do? Well, they trained actually 5 of these things, and they ensembled those results together. So like another layer of ensembling, right? And so you can see there was actually nearly 2 percentage point reduction in the top 5 error rate, and that's what was submitted to the competition and what won. You can make some slight adjustments, add more networks to your ensemble, and you can get an even better top 5 error rate of 15.3%. So this completely smashed, the records of what had been done before. Was completely, in some sense, for most people, came out of the blue that it did so well, and is really the beginning of kind of the modern neural network deep learning era. So that's it for today. We're done a little bit early, which is great. And next time we're going to talk about the next couple of years, the architectures that were submitted there, and how they're the same, how they're different, and more about why they gave improvements. So I'll stick around if any of you want to chat. Otherwise, see you on Thursday.
Why do you use top 5 errors?
It just was chosen. It's chosen because, you can see how bad the top 5 errors were for in 2010, right? Like basically 30% error. So it was hard. It was still a hard task.
And one more question: why do we have to scale the output? Because when you are scaling, the result doesn't change.
Well, what happens is that you think about this as from layer to layer. So the layer has been trained and is expecting activations or like the feature maps, those activations to be of a certain size, because that's what it's seen all throughout its training. But now all of a sudden they're too big, right? And so the network hasn't seen that, so it's not tuned to that size. So because of the nonlinearity.